In the last video we looked at ways of combining two sets to make a third set, namely the union and the intersection. And this is similar in a way to the ways we have for combining two numbers to make a third number. We have, for example, addition and multiplication. If you have two numbers, a and b, you can form a plus b or a times b. And one of the very useful things about addition and multiplication is that they obey certain rules. So, for example, if you have two numbers a and b, then a plus b is always equal to b plus a. And similarly for times, a times b is always equal to b times a. And there are even rules about how plus and times interact with one another. Specifically, we have properties like a times b plus c is equal to a times b plus a times c. So given that those arithmetic rules are so useful, it would be nice to have similar rules which govern how intersection and union behave. And that's what this video is about. We're going to develop some of the rules about intersections and unions. And we're going to start off on this slide with the commutativity and associativity properties for intersection and union. So let's begin with commutativity. So this is the commutativity property for intersection. What it says is that if you have any two sets, capital A and capital B, then A intersect B equals B intersect A. And the commutativity property for union is exactly the same thing for union. It says if you have any two sets A and B, then the union of A and B is equal to the union of B and A. So let's just think why this is true very briefly. I mean, it really follows directly from our definition of intersection and union, because just focusing on this second property, the commutativity of union, a thing x belongs to A union B, well, the definition is that that's true if and only if x is in A or x is in B. But what we mean as mathematicians when we use the word or is that one or both of the two statements here, x in A and x in B, one or both of those statements is true. And of course, for one or both of those statements to be true, it doesn't matter which way round we write them down. So equally, this is true exactly when x is in B or x is in A. Right, but that is, by definition, what it means for x to be in A union B. Now, we've argued that something is an element of A union B if and only if it is an element of B union A. Excuse me, I've written the wrong way round there. Okay, and that's what it means for two sets to be the same thing. Two sets are the same when something's an element of one of them, if and only if it's an element of the other. Okay, so that's the commutativity property. Let's look now at these associativity properties. So the associativity property for intersection is that if you take A intersect the intersection of B and C, then that set is equal to the set you get by intersecting A intersect B with C. So this is a lot easier to write down than it is to say out loud. And the associativity property for union is just exactly the same thing, only with union in place of intersection. So I'm not going to give an argument as to why this is true. If you want to convince yourself, then for this associativity property for intersection, you should just convince yourself that both of these two sets, the left-hand side and the right-hand side, are the set of things which belong to A and belong to B and belong to C. But what I will do is just say very briefly why the associativity property is useful. And it's useful because it allows us to write expressions involving intersections or expressions involving unions without having to put brackets in there to specify in which order you're supposed to compute these intersections. So you can write A intersect B intersect C, for example, knowing that it doesn't matter whether somebody works out what the set equals by doing this intersection first, or whether they work it out by doing this intersection first. So the expression A intersect B intersect C, as I've written it there, is completely unambiguous. And in fact, more generally, you can write down intersections of arbitrary length without having to put in any brackets to specify exactly what you mean. And so on. Okay, so this is really the use of associativity. It allows us to form expressions like this without having to write dozens and dozens of brackets to explain what we mean. Okay, let's now move on to some of the other laws which govern the behaviour of intersections and unions. So we're going to look at what's called the distributive laws. And those things are similar to what to the arithmetic laws I mentioned earlier, that, for example, a times b plus c is equal to a times b plus a times c. That's called distributivity of times over plus. Now, one of the interesting things about set algebra is that not only do you get a distributivity law for union over intersection, you also get a distributivity law for intersection over union. That's surprising because this thing which I've written here, this arithmetic statement, is true, but it wouldn't be true if I swapped plus and times, whereas the analogous statements is true for unions and intersections and for intersections and unions. So that's perhaps a little surprising. So anyway, let's look at what these rules actually are. So distributivity of union over intersection is the statement that for any three sets A, B and C, A union the intersection of B and C is equal to A union B intersect A union C. And the second law here, the distributivity of intersection over union, is exactly the same thing, except with unions in place of intersections. So if you want to convince yourself that those things are true, well, you have lots of different ways to do that. I mean, one popular way is to draw a Venn diagram like the one that I've put on the right-hand side of the picture there. So if you draw a Venn diagram like this, then the shaded area here represents, well, which one is it? Is it the first or the second of these two distributive laws? Pause the video and think which one it is. Okay, well, of course, this is the second. This is a picture of this second distributivity law, the distributivity of intersection over union. So if you look at this grey shaded area, then what it is the intersection of A with the area represented by B and C on this Venn diagram. And you can see also that you can obtain that grey area by taking the intersection of A and B, which is this part of the diagram here, and unioning that together with the intersection of A and C, which is this part of the diagram here. So the fact that you get the same Venn diagram when you try to illustrate the left hand and the right hand side of that law tells you that this really is an equality of sets. Those two things really are the same. Okay, but perhaps we'd like to give a more formal proof of this. So that's the last thing I'm going to do in this video. I'm going to try and give a more formal argument that the first of these two distributivity laws is true. So what we're going to do is we're going to give names to the two sets involved in this first distributivity law. We're going to call this set X, and we're going to call this set Y, and we're going to give a careful proof that X is equal to Y, so this distributivity law really is true. So when we want to prove two sets are equal, well, we have a standard way of doing that. If you want to prove that X equals Y, you prove that X is a subset of Y and Y is a subset of X. That's the most common way to prove that two sets are equal. So let's do that. So first of all, we're going to show that X is a subset of Y. And to do that, I have to take an element of X and prove that it is also an element of Y. So let's let Z be an element of X. Okay, X is A union B intersection C. So either either Z is in A or Z is in B intersect C, or both. Well, okay, if Z is in A, then for sure Z is in A union B, because if you're in A, then you're in A union anything. And what's more, Z is going to be in A union C for the same reason. So in this case, Z is in A union B, it's in A union C. If it's in both of those things, then it's in their intersection. That's what the intersection is. So it's in A union B, intersect A union C, which is Y. Okay, so in this case, Z was in Y. So what was the other possibility? Well, the possibility I haven't covered yet is what if Z is in B, intersect C? So if Z is in B, intersect C, well, this time Z is in A union B because it's in B. If it's in B intersect C, then it's in B. And if it's in B, then it's in B union anything. So it's certainly in A union B. Okay, so similarly, Z is in C. So it's in A union C, because if you're in C, you're in C union anything. So if I put those two statements together, Z is in A union B, Z is in A union C. So Z is in A union B intersect A union C. Well, that is in Y. Right, so in every case, our element of X also had to belong to Y, and therefore we've shown that every element of X is also in Y, which means X is a subset of Y. Okay, I've done half of my job. I've shown that X is a subset of Y. Let's now do the other subset relation. So my new claim is that Y is a subset of X. Okay, how do I do this? Well, we're going to do the same kind of argument. We're going to start off by picking an element of Y and then showing that that element must be in X as well. So let's have an element again called Z, which is going to be in Y. Okay, so Z is in A union B intersect A union C. That's what Y is. All right, well, again, let's split into two possibilities. This thing Z, either it's in A or it's not in A, right? Those are the only two possibilities. You're in A or you're not in A. So, first case, if Z is in A, well then, as I've said a few times now, if you're in A, then you're in A union anything. So Z is certainly in A union B intersect C, and that is the set X. Okay, so in this case, Z is in X. All right, so the other possibility is this element Z does not belong to A. So what happens if Z is not an element of A? Well, you're an element of Y and you're not in A. Well, okay, if you're an element of Y, then you're in the intersection of A union B and A union C. So you're in A union B and you're in A union C. So Z is in A union B. Z is not in A, so it must be that Z is in B. But on the other hand, again, if Z is in Y, then it's in A union C. And if it's not in A, but it is in A union C, well, then it must be that Z was in C. Okay, so let's put these last two things here together. Z is in B, Z is in C. So Z is in B intersect C. Okay, so in this case, Z is in, if it's in B intersect C, it's in B intersect C union absolutely anything. So in particular, it's in B intersect C union A, which is X. Okay. We have proved that our arbitrary element of Y is also an element of X, and that means that Y is a subset of x. Okay, we have proved x is a subset of y, we've proved y is a subset of x, and that is the definition of x being equal to y. So putting these together, x equals y. And we're done.